And welcome to Climate Chat. I'm your host, Dan Miller. And today I have a special guest, a longtime friend, Brett Henkel, who is the co founder and SVP of Svante. And we're going to find out what Svante is in just a moment. But just for full disclosure, Svante is a company that I invested in a long time ago, actually, around 2011, 2012. This was long before anyone was talking about carbon capture. It was just sort of something, an inkling of an idea, I guess, back then. And Brett's one of the folks who actually made it happen. So first of all, Brett, welcome. Great to see you.
Well, thank you very much, Dan. And just to comment on your support, that was before others were really involved in this space, and you had a vision, and your support was instrumental in Svante becoming the company it is now, and providing some tools in the climate change fight. So thank you very much for that support and your continued support, Dan.
Yeah. So, well, the reason we did it is that we looked at climate change and realized that we weren't going to make it without carbon capture. I think that's getting more obvious every day. And so we have a lot of work to do, but we're going to learn. A lot of people have a lot of doubts about carbon capture, and I think we're going to really dig into that. The title says Pulp and Paper Mills. There's a very special application there, which is very cool. But we're going to talk about carbon capture more broadly as well. But why don't we first start off with, tell us what Svante is, because I think a lot of people don't know about the company.
Sure. Svante is a CO2 capture company. We're developing technology both for smokestacks, for point source, but also for direct air capture as well. Our technology is based on a material called an adsorbent, which has been around for a while in separating other gases, over 100 years, but it's new for CO2 capture. It's much more environmentally sound than the conventional and the first generation of CO2 capture. And it can fully recyclable. It has no secondary emissions. It's simpler to operate. It's simpler to deploy. Lots of benefits, but as Dan pointed out, that he started supporting us in 2011. I founded the company in 2007. It takes a long time to develop and commercialize a new process technology for the world. It takes a lot of resources, a lot of people, a lot of support. So it's taken a while, but we are at the final stages of commercial deployment. And we see that CO2 capture is going to take off, especially in the 2030s.
Okay, so you mentioned there's something called an absorbent. So Svante's company is building carbon capture systems, you said, for point source. Just to be clear to everyone, that includes like industrial emissions, things where there's a concentrated amount of CO2 in the smokestack and the flue gas. And that's like cement and steel and pulp and paper mills and other industrial processes. So it's a lot easier. What are we talking? So we're talking about a concentration, like for cement, of 20% CO2 or something in that order.
Yeah, I mean, point source smokestack flue gas can go anywhere from about 4% all the way up to around 30%. Coal power is 13%. Cement is 16 to 20. Steam methane reformer of hydrogen is more like 20 or 22%. Just burning natural gas, just the simple process of burning natural gas give you about 8 to 10% CO2. And then turbines, especially combined cycle turbines, which give you about 4% CO2. So it depends, but it is highly concentrated depending on the fuel that you're burning, and therefore thermodynamics perspective, it's easier to go after a concentrated source and separate the CO2 from the nitrogen. That's the real technical challenge that there is. I like to make an analogy to people that It's like getting up in the morning and putting cream in your coffee and then changing your mind 10 minutes later and saying, I want to separate them. It's like that. CO2 and nitrogen, once they're together in a combustion process, they really like to be together. And getting them to separate is difficult. And we need to separate them because it's the CO2 that is the issue going into the atmosphere. It's not the nitrogen. Air is mostly nitrogen, so that's okay. But we need to separate out that CO2 because just dealing with the mixture, we can't do that. We can't put it back in the ground. It's too much. There's no other processes to deal with just the flue gas, so we need to separate that CO2 out. And that's a technical challenge to do that. That we've all been working on globally for quite some time. We believe we have a pretty good solution to do that. That doesn't impact the environment further.
So, but just to contrast the point source, you said that basically 4 to 30%. A concentration that the 4% might sound like a little bit, but in the air, CO2 is only 0.04%. I'll say that again, 0.04%, or about 400 parts per million. And so it's way more concentrated in a flue gas than in, for example, we'll talk about direct air capture later. So it makes it easier and cheaper, I assume, to
I mean, you don't have to be a rocket scientist to think that separating a small little amount out of the air is much more difficult than the concentrated source on that. So I mean, the world is working on both, and I do believe that we need to do both. We put a lot of CO2 into the atmosphere over the last few hundred years, and continue to do so every day. So there will be a need to turn back time on that and bring CO2 out of the atmosphere in the most efficient ways possible to do that. But you're right, it is much more challenging to go after the CO2 that's already in the atmosphere.
So we'll get to that later, but I really want to walk people through like how this works. I mean, people hear about carbon capture and they have there's some kind of filter or something like that. But let's talk about the Svante solution. What's going on? Like, let's start with a pulp and paper mill or a cement plant. That kind of works the same way. So walk us through it. You start with this mill and there's nothing capturing to the point where you put something on.
Start with a cement mill. Maybe easier to talk about all the different types of emissions in a cement plant. A cement plant has a kiln that heats up limestone and generally uses fossil fuel to do that heating, and it's combusted. But also CO2 comes from the limestone itself. About 60% of the CO2 comes from the limestone itself. That's released, called process CO2, process emissions on that. So it's a combination of burning fossil fuels. Maybe about 40% is from that, and 60% is from the limestone itself. That all gets collected together, all into the same pipe, and then that is sent to the smokestack that you see. That if you have looked out the window at a cement plant, you'll see a smokestack, and a very, very large one. That is all collected and gone up to that smokestack, and it runs in at about 16% CO2, as I said before. Now, to do CO2 capture, you don't let it go to the smokestack first. You divert that flow before it goes up the smokestack, and you put it through a process where you can separate the CO2 and the nitrogen. And by the way, you also separate some of the other nasties at the same time. So that's a benefit of CO2 capture that I think has not been talked about all that much. Going after CO2 inherently means that you're actually scrubbing more than just CO2. You're scrubbing SOx, NOx, and other types of particulate and others.
Nitrous oxide.
You're inherently scrubbing the other kind of stuff that we don't like going into the atmosphere that we're already trying to control, but this even further reduces those emissions. So there's an added benefit there. But the key is to separate that CO2 and now have a pure stream of CO2, and the nitrogen can then go back up the stack and go out. That's the bulk of the flow, right? That's in a cement situation, that's 84% of the flow just keeps going up the stack and goes into the air, and that's fine. But now you have a pure stream of CO2 that we can tackle, and in different ways. We can, and I would say the start of CO2 capture, most projects take that CO2 and find a way to put it back into the ground where it came from. And that's called sequestration. It's been done for quite some time now. It can't happen everywhere, but it fits very industrialized places, usually have the capability of doing sequestration, and you can be put it back on the ground. But there's other things we can do with CO2 as well. We can take CO2 and inject it into concrete and trap it into concrete. It can't be transformed into other things. It can also be combined with clean hydrogen and formed into a fuel,
right?
And has another life. That's called, the most recognizable term on that is sustainable aviation fuel. That's a combination of captured CO2 and clean hydrogen, and you can put those together and produce a liquid hydrocarbon.
Right.
So there's a lot of things you can do with CO2 to make sure it doesn't go into the atmosphere. Okay, but that capture part, meaning the separation of the CO2 and the nitrogen, is challenging, and that's where Svante comes in with new technology. It looks like a filter. It's an adsorbent. It's a material that traps CO2 but doesn't trap nitrogen. And those are new materials. And we continue working on new materials to do that in a better and better way, more efficient way. Where there's energy needed to do that is when that material grabs onto that CO2 molecule, it then needs to be released off it because it likes it. It grabs onto it and holds it. It doesn't hold the nitrogen molecule. It holds the CO2 molecule. Right. And then we have to put in some energy, some heat energy to release it off that off the adsorbent molecule and now have pure CO2. And that's where the energy comes into it. That energy can be in different forms. It often is in the form of steam to produce that heat.
So you have a filter material. Actually, I've seen it. It looks like a air filter, but it's black. Yes. But it looks like an air filter with lots of channels for the air to flow through.
Actually, the new ones are even white, so it very much looks like an air filter. You could hardly tell the difference looking at it.
Okay, but the property of it is that it holds on to CO2 when it's cool.
Yeah,
and then it releases it when it's warm.
100% exactly. Yeah.
So now you start with that, and then you have to build a system around that to cool the filters, allow the CO2 to stick to it, and then put steam in there to knock it out, and then start the whole thing over again, right? Is that?
That's exactly right. Yeah, we need to cool the flue gas for starters, because the process can't work at hot temperatures, and flue gas is usually quite hot, right? So there's a lot of heat there. The key to that heat is to use it. I mentioned that we need heat to release that CO2 off the adsorbent. Well, there's a lot of heat in the flue gas, and we work really, really hard on using that heat. That what we call is used. It's usually waste heat. It's not used. It's just gone into the atmosphere.
Going up the flue gas. It's going up the chimney.
Flue gas. It's often actually a problem in the area, that hot gas. And we use that heat to drive the process. And I would say almost all of our projects now utilize waste heat that's already at the plant to drive the process. And that's a much better way. There is projects out there that produce that heat to do the regeneration. Maybe I'll back up, and we've explained, Dan and I have explained the Svante technology is based on a solid adsorbent that does this. But older technology works in a similar way, but it's a liquid. It's called a liquid amine. This amine is fairly nasty chemical.
Yeah.
It works for sure, and we've built the world has built big plants based on it, but it's a fairly nasty chemical, and there's been projects built in the world where the steam or the heat needed to get the CO2 off that liquid is derived from burning more fossil fuels.
Right.
Right. And that's that's a tough one, right? Because you burn more fossil fuels, you produce more CO2, and you're kind of chasing your tail a bit on that.
Although the system does capture it if you build the system right.
Oh, absolutely. And you can capture
you have
that.
to build a bigger system because you're not just capturing from the original.
Yeah. But you want to reduce that as much as possible, right?
Exactly.
You want to get that down. You want to use waste heat wherever you can to do that. And so most projects are moving in that direction of using the existing waste heat as much as possible to drive the process.
And in pulp and paper, you actually have more than enough waste heat, so you really don't use any fossil fuels in that application. Is that right?
Yeah. Well, pulp and paper is this really interesting application. So we have described two scenarios that seem quite different, right? We're talking about point source carbon capture, and we're talking about the burning of fossil fuels, and then capturing that CO2 and doing something with it, making sure it doesn't go into the atmosphere. We also described taking CO2 out of the air, and direct air capture on that.
Right.
The interesting, I think, actually, the really compelling feature of pulp and paper, and there's some other processes too that I'll talk about that are the same as this, is that the carbon dioxide or the carbon that we're talking about capturing in a pulp and paper smokestack originally came from the air.
Right.
so how that happened is that the trees, the wonderful natural way of growing trees and photosynthesis actually took carbon from the atmosphere to do that, right? And grew and trapped that carbon in the tree itself. And in the pulp and paper process, while you're making and taking biomass from the forest, and by the way, it's in a very sustainable way. In any projects that CO2 capture is looked at, the biomass system has to be sustainable, and it can't be, and that, so that's the first thing always to look at in these projects, is that the forestry management is sustainable. But that biomass comes in, it's then turned into pulp and paper, but there's some residuals that are left, that is biomass, and that is what is burned to create energy at the site, to drive the entire site and the processes. Mm-hmm. And so that,
including electricity, is that right?
Including electricity, absolutely. Right. All of the power, all of the heat needed at that site is derived from that biomass residuals. So if we capture the CO2 from that smokestack, it actually is carbon removal. It is direct air capture. Really, it just takes longer because it has to go through the trees. But really, that carbon is coming from the atmosphere. So it's called negative emissions, and it's really compelling because of that, right? It's actually taking CO2 out of the atmosphere. And also, as you mentioned, Dan, the other really compelling feature of that project is that all of that power or electricity and heat that is needed for the capture system is clean. It's not derived from fossil fuels, right? So it's not contributing to CO2 into the atmosphere. So that's an added
renewable energy.
It's renewable energy at site, right at site. You don't even have to bring it in. You don't have to take it from another project. It's there already.
Self-contained.
It's self-contained. So quite compelling. I would say it's an in-between step that the world should go after first, right? There's limited resources in the world to tackle climate change, right? And that's the struggle. There should be more. We all want there to be more directed towards it, but there's a limited amount. Where should that go is always the question. When you're looking at CO2 capture, the bioenergy CO2 capture should be the first places resources should go, because that's the biggest bang for the buck. You actually get a negative emission. There's limited impact to the renewable system, because you're not taking renewables from other places, and also it's truly sustainable,
Well, it's even better than sustainable. It's negative emissions. So that's
negative emissions, but I'm talking about the process itself of getting that CO2 from the forest, right? Those trees are going to keep growing. They're going to grow over, and they're planted. They're going to grow over and over. As opposed to if you're talking about capturing from a cement plant, the limestone and the fossil fuel that you're using to do that isn't truly sustainable. There will be a limit. We don't know when that is going to be, but there will be a limit, right? Whereas you're talking the pulp and paper, and there's other types of projects that are similar to the pulp and paper. There is waste to energy. Now, we're not as familiar with waste to energy here in North America as Europeans are. There is 500 waste to energy plants in Europe, approximately.
Basically power plants that make electricity from burning garbage, basically.
Exactly. Yes. And they're very good at it. They're very efficient plants. They're very good at this. And about 60% of the garbage that they burn is biomass. Therefore, the carbon that is burnt, or the carbon that is derived in that flue gas coming out, actually 60% of it came from the air in the first place, right? So you could think of that as a very complex direct air capture process too, where something gets turned into a product, but it has a biomass component to it. We use it, and then we dispose of it into garbage, and then it gets burnt. And then we capture the CO2 from that and capture the carbon and make sure it doesn't go in the atmosphere. So it's more complex, but it is direct air capture as well. So that's another big application that has this wonderful feature of being negative emissions. Okay. By the way, cement has that too. Remember I said that 60% of the cement is from the limestone, which is very difficult to deal with. And that's why I believe that CO2 capture is the number one tool for cement, because we don't know how to make cement on the scale we do without limestone. So it's hard.
Because even if instead of using fossil fuels to heat the cement, let's say you used renewable energy somehow to heat the cement, you're still going to have 60%. Well,
still have 60%.
Lot, over half the emissions just
100%.
from the chemical reaction.
That's why I think CO2 capture is the number one tool for cement. But that 40%, many cement plants are turning, instead of burning a fossil fuel like coal, which they traditionally did, they switched to natural gas. Now they're switching to biomass. There is plenty of biomass, and they're switching to waste biomass. So really that garbage component that the waste energy plants use, the cement plants are switching to using that biomass component. So 40% of the output of that cement plant can be from a biomass component, meaning that part of it is negative emissions if it's captured and doesn't go into the atmosphere. So there's a really compelling component to the cement. So it takes two things to do. First, you switch that 40% from fossil fuel, right? And you use biomass to drive that. And that's happening. Many European cement plants do that already. The one here, I'm in British Columbia in the Lower Mainland. There's a cement plant in Richmond that the British Columbia government helped them switch over. Now they're at 50% biomass, 50% of fossil fuel burning for that 40% of CO2 that's made. So really good start. They're pushing towards 75 and even 100 in the future. Therefore, if we captured the CO2 from that from that plant, all of it, then we would have a 40% component of negative emissions.
Well, I understand it's even better than that, because once you make cement, from that moment onward, the cement is absorbing CO2 over its lifetime.
Yes,
especially if you break it up eventually, because it is into the pores and things. And so
it's slow, but that's a component of cement as well. Yeah.
So if you capture all the CO2 from the making of it, then the cement itself, this is putting aside the biogenic fuel in the plant, the cement itself will absorb CO2 over its lifetime. So you have negative emissions that way too. But that's one that I almost never see talked about.
No, it's not talked about. It's really not talked about.
It was surprising to me when I learned about it. And
they're either talking about biomass switching in a cement plant. They talk about that on its own, or they talk about CO2 capture. The combination of those two things is very rarely talked about, and it's I think it's very exciting, actually. Yeah. That combination.
So maybe we could talk about a little bit what this thing looks like. Here's a slide from the Svante website. By the way, there's links to Svante and to Twitter links and things like that as well. But you can get to this if you'd like. It's under the technology section, I think. So maybe you can tell us what we're looking at here.
Yeah, absolutely. This is a large wheel. We make two
merry-go-round.
Yeah, it's kind of like a merry-go-round. It does, and it spins about the same speed. It's about 1 cycle per minute. So you could imagine getting on it. We should charge for rides, maybe. But they're fairly large. They're 14 meters. This one's 14 meters. We have a 24-meter
one. A person standing here.
Well, exactly. And why we have a wheel here that's doing this, you have to imagine in this picture there being ducting on the top and ducting on the bottom, bringing gases in and out. Okay. Right. So what we described before is a process that where this material takes in the flue gas, grabs onto the CO2, but not the nitrogen, and then it needs to be heated, and we do that heating with steam. Okay, so it's a batch process, right? It's a actually there's one more step where you put air into it to cool it. So it's actually a 3-step process, right? And that's what this wheel does, actually. It carries these filters, which the little blue boxes that you can right see here, those big boxes are full of the filters, okay? Yeah. What the wheel does is carries the filters through the 3 steps. So it carries the filters through while they're getting filled up with CO2, carrying it through the flue gas. Mm-hmm. Then once that filter is full of CO2, it can only take so much. It can take a lot, but only so much. It gets filled. Then it goes into the steam step where the steam is coming through and stripping off that CO2. You then condense the steam. Steam is just water. You condense the steam and you're left with pure CO2 or close to pure CO2, 96% CO2 and above. And then the wheel carries the filters into the air step where it's cooled back down and ready for the flue gas again. So on the outside, these are continuous flows going in and out. Mm-hmm. On the inside, it's a batch process where the filter is being carried through those steps by the wheel. So that's what the wheel is doing. Fairly a simple process once it's running. Once you have the material in there and the filters in there, it's fairly simple. To have less flue gas go through, all you do is slow down the rotation speed of the wheel, to process less. To turn it off, you just stop the wheel from spinning and everything stops. To turn it on, you start the wheel from spinning and start putting the flows through, and it works. So it's quite a quite flexible, quite simple operation. Can load follow with operations that have to stop and start and turn up and down quite a bit. So, and that's it. And you can tailor the filters and the material to the different applications that you're using. So, most of our applications that we're going after right now are pulp and paper. That's for the reasons that we all already discussed. They're very attractive CO2 capture. They're plants that are already. There's no plans on shutting down those pulp and paper plants. They will, they're sustainable.
They're running anyway.
They're running anyway. They're going to keep running. There's zero plans to shut them down. And if we can put CO2 capture on those, we got wonderful negative emission systems that are running and capturing CO2 out of the atmosphere, and that can happen for the foreseeable future. Right.
And that's also there's a name for that. It's actually BECCS, right? Yes. Bioenergy and with carbon capture and sequestration.
That's right.
And a lot of people think that's not a real thing, just made up by the IPCC as a. But it is a real thing. And
it is absolutely a real thing. And there's quite a bit of biomass in the world. And it's not being used either. There's even one project we're working on where they're going in after logging and taking biomass that is usually burnt at the cut block, believe it or not. They stack the trees up that aren't taken to the mills,
Yeah.
and then they burn them in the wintertime, which
Oh.
produces CO2 that goes into the atmosphere and just is a total waste of that energy. So there's companies that are figuring out how to take that biomass in, and produce power with that biomass, but capture the CO2 as well. So
So for the typical pulp and paper mill,
Yep.
how much total CO2 are we talking about capturing in, let's say, a year?
Well, they're pulp and paper plants. Why they're another reason they're a good target is they're quite large. They produce a lot of CO2. A typical pulp and paper plant can be 1 million tons a year.
Million tons of CO2
a million tons a year, and not all of that is bio-based, but the majority of it is. So if a pulp and paper plant is producing 1 million tons a year, in and around 700 or 800,000 of that will be bio-based, meaning that the carbon in that flue gas will be coming originally from the atmosphere. Now, they burn a little bit of fossil fuel here and there for some reasons. They need to make lime, so they burn natural gas to make some lime for the process. In some heaters and whatnot, there's some natural gas. They're trying to get away from that. They're trying to bump up the bio energy that they use. But in general, the majority of that CO2 is bio CO2 that came from the atmosphere in the first place. So that's why they're a great target. An 800,000 ton per year CO2 capture project is a really nice size because it's economies of scale. It's big. It has impact. It has real numbers behind it. It's not just,
that's a lot of CO2.
A lot of CO2.
So people talk about other things, and
when you talk about the capacity are very small, right? And it's a mind-boggling how big a challenge we all have in front of us when you're talking 40 gigatons a year that we're putting out into the atmosphere. So it's really good to have these tools that can have big impacts. Like 800,000 tons per year project has a big impact, and if that's happening every year, forever.
Okay. Well, and also a cement plant is also like 1 million or even more.
Yes. Unfortunately, a cement plant is 2, and that's a lot of that is
huge amount. In fact, in total, all of these. So if we just look at the amount of CO2 that humans emit, it's about 40 gigatons a year from the fossil fuel industrial. Everything. And of that, about 25% of it is industrial emissions. Like another 10 is like electricity generation. That's the part everyone focuses on. We had Bill McKibben talking about solar power a week and a half ago, which is incredible how fast that's growing. But that's mostly at this point for electricity generation to replace fossil fuels. But if you replaced 100% of fossil fuels for that, you'd remove
still wouldn't be there, right?
10 gigatons. But there's another 10 sitting in these plants that if you don't do carbon capture, and we still make cement, we still make steel, we still make paper, these emissions are going to continue.
We have Elon Musk in the world, and we have the incredible growth of renewable power, which kind of has gotten everybody very familiar with those types of greenhouse gas mitigation,
cars and solar panels. And
what I like to explain to people is there's 4 general buckets of CO2 emissions that make up that 40 gigatons. Some of them we're very familiar with, some of them we aren't. So the ones that we know, we all know, and we all talk about it a lot. There's transportation, right? Planes, trains, automobiles, you name it, right? And we burn lots of fossil fuel in there. We understand that pretty intimately. We know internal combustion engines, and we also know the potential to change that. That's happening, and I would say it's quite encouraging. The emergence of electric vehicles and fuel cell vehicles. And fuel switching and lots of paths forward on that. And I would say the general public knows that quite well, right? Not everybody agrees with it, of course, but I would say there's quite a bit of knowledge around that. Same with power. Because of wind, because of solar, because of the discussion around nuclear, I would say that the other big bucket of power production and CO2 emissions from power production is quite well understood.
Electricity power production.
Electricity power, yeah. And we have fantastic tools to do that. Now, change is hard. Change usually costs money. And to change our electricity systems overnight is very, very challenging, especially in developing countries, like India. But it's happening, and it's happening on a global scale. We're changing from using coal power and fossil fuel power over to using renewables power. That's wonderful. People understand that. But the next bucket is way less understood, and it is really because we rely in modern society on the products that we use every day, and it's difficult to understand how the floor that you might be standing on right now that's made of concrete, how that impacted and where the CO2 come from. It's not as easy to think about that. Or when you get into your car and you see the plastic and you see the metal in that car, and to relate that to, oh, well, how much CO2 did that produce while it was being made? That's not well understood, right? The general public doesn't understand that link, although I believe that is very, very difficult now, since we're all so used to it for so many decades or even centuries now, that the use of steel, the use of concrete, even the use of plastic, and by the way, even think about fertilizers. Fertilizers to feed 8 billion people mostly comes from fossil fuels. And if you've ever been to a fertilizer production plant, there's a whole bunch of smokestacks. So we're kind of married to these products that we use every day, right? Like every day, no one can get away from using some of these products, right? We use them, and I don't see any plans to stop producing those types of products. And the challenge that the world has had is that to make those products in a way that doesn't produce CO2 is extremely technically challenging. So much so that I would say there's not even any really good paths forward to doing that in most of these products. Like cement, to make cement without limestone, yes, there's some ways, but they're so far in the future, and they're at a low scale right now that it's hard to imagine how to switch over. Same with steel, same with plastic, same with most of the products that we use all the time. And this is what's not understood: how large a component of the greenhouse gas emissions those products are. It's a very large component. You could talk, depending on whether you're talking about agriculture emissions or not, but you could easily talk about 25% of the emissions are from the products that we use. That many. So we're talking in the scale of 15 gigatons a year, that much,
right?
And so that's why CO2 capture, even though it has a lot of pushback from people, because it's a pretty big change and a pretty big challenge. It takes money, it takes resources to develop. It has never gone away, because going after those 10 or 15 gigatons from industrial emissions, there's not that many options. And I don't see anyone talking about turning the cement plants off.
Right, because you also need them to build the windmills and to put the solar panels in the ground, and you put them on concrete footings and things like that. So,
I mean, we wish we could. We all do. We all wish we could just turn them off, turn those smokestacks off, and make it in a different way, right?
Yeah.
But that's not how physics works.
Well, you'd also have to rebuild every cement plant in the world, which, it's not going to happen anytime soon.
It's just we've figured out for hundreds of years how to make these products in the best, most economical way possible, right?
Mm-hmm.
And to suddenly switch and making stuff in a different way is just not. It's not possible in decades, right? Maybe in 100 years it might be possible to switch some of them. We're pretty smart. We can figure stuff out fairly quickly, but not in decades when it comes to industrial processes. It takes a long, long time, and we don't have that time. Dan, you're probably the more of the expert on saying how much time we have.
Way less time than people think. We're at 1.5 degrees already, and we're seeing the impacts of that. And there's some feeling we could be at 2 degrees in the 2030s, and certainly by the 2040s, not the 2030s. And that's not going to be pretty. So yeah. So you mentioned that there's some people have some doubts about these things. So I made a little list of the complaints people make about
sure you
carbon
could make
capture.
a long list, Dan.
Well, it's not that long, but they're pretty fundamental. So the first one is it doesn't work. It's a scam. It doesn't really capture. It doesn't work. You've been running systems for a long time that they're actually capturing CO2. Is that right?
Yeah, I mean, separating CO2 and nitrogen can be done. And it has been done for a long time,
like 50 years or something.
Yeah, there's no, in my mind, that is not the question of does it work. It works, absolutely works.
Oh, by the way, let's talk about what there was one thing though, and we'll maybe get into this a little bit later. But Mark Jacobson, which we've interviewed on the show, and Robert Hillworth, which we've also interviewed on the show here, wrote a paper a few years ago that said CO2 capture is a scam. For a bunch of reasons, and they used numbers in it. And one of the numbers they used was, I think, it only captures like 65% of the CO2. So what's the real number? A real system that you've built, what percentage of the CO2 flowing through the flue gas is captured by the system?
Yeah.
In reality.
Let me just finish the comment on does it work. Technically, it works, and you can do it. You can separate CO2 from nitrogen. Absolutely, you have been for a long time. At what cost is the real question to do that?
Well, I was going to get to that too.
That's the real question, right? At what cost, and does it make sense compared to the other ways of mitigating? You know, that's the real question, and it's a super valid question. Absolutely.
Yeah.
Now, what you're talking about, and there are quite a few papers came out in the last few years, and there was concern about capture rate. Okay, you know, say 1 million tons a year is coming off that cement plant. And, you know, you put in a carbon capture plant and, well, you only get 50% of it. And you spent all this money and you only get 50% of it or 40% of it, or maybe even lower. That was the concern. And that's what some papers came out with. And then some projects kind of, to be fair, did show that. You know, they were built and they captured just a fraction or a percentage of the total emissions of that plant. Now, but when you dive deep into those plants and look at what the objectives was for those projects, because this is this industry of CO2 capture is still in its infancy and just emerging, we often decide not to capture all of the CO2 from that plant because we're doing a smaller project. We're reducing cost because
it's like a demonstration.
It's a demonstration. And so we don't want to go after the whole thing because it costs too much right now. And the policy framework isn't in place to pay for the whole thing. But we want to demonstrate that it can be done. So we go after capturing a portion. I actually had CTV News come in last month. And an anchor at CTV News, surprisingly, I won't name names, but you can look at it. Actually, if you look up CTV, it's now an actual a news article out there. But they came in with this exact issue. They said, "Oh, you tried to capture CO2 at the Lafarge cement plant here, but you only ended up capturing 1 ton per day, and it releases about 1,500 tons per day. So your technology doesn't work." Really?
Yeah.
That was the thought, right? And I had to spend, you know.
But what's it? Well, before you go any further, why was it only 1 ton out of 1,500?
Yeah, that's what I had to explain. Is that we wanted to demonstrate that we could capture CO2 from that, but not spend tens of millions of dollars. We didn't have that money. We just wanted to show that it would work. So we took a slipstream, a small little piece of the flue gas, right, that had about, you know, 1.2 tons in it, in that flue gas slipstream, and we captured 1 ton, right? So what I had to explain is that we captured 90% of what we tried to capture,
Mm-hmm.
And that's what we were showing. And many projects, even at a bigger scale, when they only captured 60% of the CO2 of that plant, they were only trying to capture 62% or 60%, right? They didn't try to capture 100% in that project. And that's where the confusion happened. And that's where it got really kind of confused. So CTV News, they thought that since we were demonstrating the technology, that we were demonstrating it at full scale. That's what they thought.
And it was a tiny demonstration.
And that's not the case. We were actually, almost all demonstrations in the world only demonstrate a small fraction of the flue gas.
So far. Well, that's going to get to some other, but before we go further, so the answer is of the
90%
90%
is easy.
Yeah.
And it happens all over the place. And we can show all of our projects and all of everybody else's projects. The goal is to get to 95 for everybody.
So 90 to 95% is how much of the total CO2 coming out of the flue gas you can capture. Okay, because those papers back then were using some of these other numbers and made it look worse. Okay, so
you know, and in that particular paper, it was on a steam methane reformer plant that has two separate streams, and the project only went after one of the streams.
Right. Yeah, it was like only half the plant or something. And
so it inherently was only half of the flue gas that it went after, right? But the paper said that it was only 50% of the total, which was true. I mean, it wasn't lying in the numbers, but it wasn't mentioning the objective was only 50%.
And so it was only the system was only applied to half the plant.
Yeah. If it was applied to the full plant, you'd get your 90 or 95, right?
So one of the other complaints, kind of related to this actually, is that if you look at all the CO2 collected by carbon capture today, it's 3 seconds a year of emissions. I don't know, whatever the number is. It's like ridiculously small compared to the 40 gigatons of emissions. And that's true, but you're kind of talking about it, right? I mean, this is basically because we haven't scaled up carbon capture yet. We're still demonstrating it. We're still building first of a kind plants and things like that. Is that right?
That's right. I would say there's two main reasons. There's more, but two main reasons is that, it's still in development. It hasn't been deployed commercially on a full scale very much. There's a handful of plants out there. So it's scary for everybody, right? It's scary for conservative industries. Most emission companies are very conservative. I mean, a cement plant hasn't changed their processes for 100 years. They don't do things different, right? It's hard for them to embrace this. It's hard for everyone to embrace this change and grab on. So it takes time. The other part is that I would say the policy frameworks to make it happen are also difficult for us, right? That's more about psychology. It's more about society tackling climate change. How much resources do we put towards it? It's very much, I make the analogy towards waste management, garbage, sewage, is that, hundreds of years ago, we didn't really deal with that either. It kind of went out our window or in the street or, we didn't really think about it because, it wasn't really a problem yet. Then it became a problem. And then society as a whole dealt with it. And right now, I bet you I could ask Dan how much you pay for your garbage removal, and you might not know.
I have a decent idea.
You might have an idea, but most people wouldn't.
Or something. It's a lot, actually.
Most people wouldn't. It's just part of their life, and they accept it, and it happens, and it's integrated into society, right? Now that hasn't happened with CO2 capture, right? The CO2 going into the atmosphere, we haven't figured out a way to have policy framework that integrates it into society to make it happen, right? And so those two reasons.
Another way is saying it. What you're saying is that carbon capture is waste disposal. That's what it is. That's
what I'm saying.
And we do agree to pay for it when it's our garbage can, but right now it's free to pollute in the air. And people are wondering why hasn't carbon capture scaled up? Well, why would you pay for waste disposal when you're allowed to throw your garbage in the other person's yard for free? And which is essentially what putting CO2 in the air is doing. And that's really the big question. Like, so let me ask you a question. If society somehow, government's policy required carbon capture or paid for it somehow, can carbon capture scale up at that point?
Absolutely. Carbon capture can scale up and be one of the key tools. Not the only tool. There's many tools, right? But it can be part of the key tools that we deploy to have a really big impact, to have a gigatons per year impact on it. And what I like
only
to
1,000 systems, right? A
Yeah,
million tons.
exactly.
Million tons a year of cement plants. If you put every,
Yes.
I don't know how many there are, but there's a lot. If throw that in with pulp and paper,
There's a
you put
lot
1,000
of
systems.
plants out there. There's lots of
What was that?
smokestacks. There's a lot of smokestacks.
There's a lot of
A lot.
smokestacks. That's true.
Yeah,
Okay.
and what I like to point out to people is that in North America we emit per capita, per person, in and around 15 to 20 tons per year.
Right, per person.
Right,
Yeah, per person.
every person distributed to Europe is much less. It's in the 5 to 10 region, and it depends on where you are in the world. But North America is particularly high, right? Because we use
Right.
a lot of energy. And if you imagine that we can get to $100 a ton for CO2 capture, right? And I think that's very doable. I wouldn't say we're there yet. Not quite, because we haven't deployed very much, so we haven't gone down that learning curve as far as we should. But I think $100 a ton is very reasonable. So if you're at 15 tons a year for every person, you're at $1,500 a ton, $1,500 a person, right? Which doesn't sound like a lot, $1,500 a person, but it is to change that into society. But it is very similar to what we pay for sewage and garbage removal.
Yeah. Okay.
It's not that much different.
All
It's
right.
very similar, right? It's not nothing. It is a change.
Well, let's talk about that a little bit, the cost, because one of the complaints is that carbon capture is too expensive, and we are talking about first of a kind systems. But let's say we do put policies in place and it does scale up to let's say to a gigaton.
Oh yeah.
What do you think
we're,
the cost?
We're going from on that down.
Yeah, no, but let's say we're at the we get up to that point, which is a first big step on the way. What do you think the overall cost of carbon capture from a point source would be if we scaled to this sort of gigaton level?
I think $100 a ton is a very reasonable average. It depends on the site a lot, the application, the capacity of the project. There's a lot of things that come into changing the cost. But I think
heat is available is one of them, right?
Exactly. Yeah, I think if you've had in your mind in and around $100 a ton in the future for CO2 capture, that would be a reasonable number. Now, what's benchmarking and what people can want? I've been asked this question probably, I mean, so many times over the last 20 years, it's just shocking, right? Now, there is a benchmark right now that you can watch, right? And it's a very valid benchmark right now that you can watch. Before, it was always someone's idea or someone's projection or someone's want. It was hard to really benchmark CO2 capture costs before, because people weren't paying for it. Therefore, was it the true cost? I don't know. It's was pretty controversial. Now there's the carbon dioxide removal credit market. Okay.
Right.
There's a credit market. These are real projects that they're being paid for, and they're announcing the prices that they're paying for them. Right. So you can watch. Everybody globally can watch this. It's companies like Microsoft that are doing this right now. They're paying for point source projects. So the pulp and paper projects that I'm talking about, the waste to energy projects that I'm talking about, right? So the negative emissions projects they're paying for. And that is benchmarking the cost of CO2 capture right now. It is by far the best benchmark of capture cost there is, because it's real money. And these companies that are buying carbon dioxide removal credits, they go deep into the project to find out the real costs. It's not arbitrary. It's not guessed. It's not a negotiation. They find out the real costs and what it takes to make that project go forward. So that's benchmarking the projects, and they're generally in around 150 to 250 US dollars per ton right now.
And that's today at small scale, sort of initial systems,
high risks.
I always tell it, like if you bought let's say a Mercedes, and that you bought the one-off prototype, it would cost I don't know, $50 million or something like that. But then once they're making a lot of them, and then the price gets
so I mean, industrial processors aren't quite the same.
They're not that
so
kind
there's not that huge as big of
but it is two or three
times,
but isn't it? Yeah.
I think so, yes, and that's why I'm saying $100 is very reasonable. I think in the best case scenario, in the 2030s, 2040s, we could even be pushing down to the $50 per ton, which makes it, I believe, when you look at the numbers for society, I think it makes it very reasonable that we can use that tool to have gigaton effects in reduction of greenhouse gases.
So another complaint about carbon capture, which you're kind of bringing up right here, is that even at $50 a ton, but certainly at 100, it's cheaper to quote limit CO2 by building renewables. Like, in other words, if I have $1 to spend or $10 million to spend, I could build a carbon capture plant and capture it, let's say $100 a ton. But if I build renewable energy, that's going to, they think it's going, it actually hasn't reduced emissions at all, but they think they can reduce emissions at a much, much, much lower cost. I kind of gave a little hint away there, but do you want to?
I have a comment on that. Well, for one thing, we need more power all the time. So we're not really reducing emissions because we're just using that more power, right? Especially when
I think 100% of renewable energy so far has gone to new energy supply.
Exactly, and that demand for that power is going through the roof. We are electrifying our transportation fleet. Imagine how much power that's going to use. Or you don't have to imagine, you can just do the math if you want.
Right.
But now the little bit more imagining is AI and what that's going to use in the future, right? I mean, the projections are kind of a little bit all over the map, but we know it's going to use quite a bit, right? And we're going to electrify. So new power is going to be soaked up pretty quickly, right? In the meantime, we still have all those industrial emissions being
cement, steel, paper, everything. Yeah.
And we're going to use more of those products.
It's also this idea that if you build first of all, I think all of carbon capture is 1% of the money going into renewables. So it's not really competing in any sense at all.
We have to do both.
So it's the assumption that there's a finite budget for saving civilization, which I always find fascinating, as if why spend money on this climate solution when you could spend it on this more efficient one? But I say, instead of like taking away from the second climate solution, why not take it away from building cruise ships or golf carts or Tupperware or we make so many things that create emissions.
Absolutely.
And if you really want to trade off and build more renewables, take it away from.
I would imagine, right? A little bit harder conversation with that one, right?
Right, but
no, that's not a conversation that very many people want to have.
No, but people think there's some reason you're only allowed to trade off climate solutions. You're not allowed to trade off anything else. We're going to do what we're doing and build all the cruise ships forevermore, rather than actually get serious about, if we need more renewables. First of all, we can build more renewables if we need to. Carbon capture doesn't stop that at all.
And let me comment on the cost of that. And I agree that some of the low-hanging fruit, that meaning that the lower cost CO2 reduction activities have happened in the last 10 to 20 years. And that's smart. That makes sense, right?
Oh, absolutely.
Efficiency gains, for one thing. Let's stop wasting so much energy, in the first place. That's very helpful, and it can do a lot more of that. But you do come to a point with all of these other activities where it gets much more expensive to go forward, to keep going. And we're seeing that a bit in renewables, is that, to go after the first 40% of electricity, or maybe even higher, it is fairly easy to do that and change the electricity grid. But going, changing it to 100% to renewables gets much, much more expensive, because you have to make sure you have firm power, and
batteries are getting cheap,
whatnot. I don't think the costs of CO2 reductions, when you look at the total outcomes of all of the different functions, are all that much different. Mm-hmm. I think in the end, they come out fairly similar, all of them, and they all have to be done in those ways because the different ways, right? I mean, transportation sector taking out the CO2 and that is very different than the power sector. And the power sector is very different than the industrial sector. But it doesn't mean that one happens and the other one doesn't happen, because that's not going to help us. So I think they all have to go forward, and they are all going forward to a certain extent. I do think that because the industrial sector hasn't been, we don't have Musks in the industrial sector. We don't have, it's not as easily understood, and not it's frankly it's not as sexy, as a cool car that goes really fast, so it's harder, and it's taken a little bit more time to develop, but I think it's coming. The policy frameworks are almost in place. They got sidetracked a little bit with inflation, and some of the
there are actually things called 45Q in the United States. There are these incentives to offset the cost of carbon capture. Right. Yeah.
And they're very close. They're very close in Canada, in the US, in Europe. Asia's coming. They're very close to making it deployable on a large scale, right? I would say the inflationary COVID and then inflation, it pushed it back a bit for the policy framework, because the policy frameworks haven't kept up with inflation. That's an issue, right? But I would say we're very close to having frameworks in place that allow for wide scale adoption, and that's coming in. I believe those changes are going to happen. Those tweaks to make it work for everybody is going to happen in the sometime close to the 2030 time frame. And that's where we want to be ready. We want to be ready to deploy on a grand scale, right? To deploy many projects every year, so we can start that number of CO2 reductions just exponentially growing.
Okay. Yeah. So let's finish up on this list of complaints about or myths about carbon capture. And that last one is sort of getting back to what Mark Jacobson and Robert Howarth put in their paper, and that CO2 carbon capture of this type, they say it emits more CO2 than it captures. Again, they use numbers like 60% capture rate. They assumed it was all powered by fossil natural gas with large leakage rates. So they said, the warming you get from, and this would be the extra energy, just from the carbon capture system. If you powered 100% by natural gas, then you would have some leakage rate, which causes, and they said that's more than this little bit of capture that the system was doing, because again, they underplayed how much capture there was. But do you want to just comment on that in general? And also, of course, how does that relate to pulp and paper? Because it doesn't use any.
Yeah, I mean, if that's the objective to show that, you can pick and choose numbers that you want to show a certain agenda. But if you use reasonable numbers, and you use the true capture rates that the whole entire industry can do, and then you do the proper analysis on the life cycle analysis on how much CO2 is released by the steel production in the plant, how much is released by everything that you do to create that system, then you can easily do that math and come out that it's a very positive gain. If you're capturing 1 million tons a year, do you get the full benefit of 1 million tons a year? No, you don't. You can't, right? Because any activity we do, right now, especially right now, any activity we do has a CO2 footprint, right? Anything,
right, including building the carbon capture system.
100%.
Like building an EV has a carbon.
Exactly. Yeah. So that has to be taken into account, and it does right now. And then generally, a 1 million ton per year plant will be, the benefit will be, maybe 750,000 or 800,000 tons per year will be the true benefit of that plant. So there's
a pretty big benefit versus
it's right now it's zero. Right now it is zero. And we're going, you're capturing, now you're having 800,000 ton per year benefit. I think it's that makes a lot of sense. The other part is that all of the different industries have to be tackled to reduce their emissions. So right now, when we do that calculation of how much the steel footprint is for putting the steel in that project, it's using today's numbers, right? The steel industry itself has to reduce their CO2.
Right.
And the issue about the natural gas and the extraction of natural gas and releasing methane during that extraction, and that methane is, what is it? 29 times more powerful than CO2, or
actually
something.
120 times while it's in the atmosphere.
120. Okay. Yeah. It's
only
a crazy
30 times over 100 years, but over 20-year time frame, it's about 86 times. So it's
okay. So it's a huge number, and it's really bad, right, for that happening. And it is happening right now with natural gas extraction. There's leakage points, but that has to be tackled. And it can be. There's a lot of pathways to do that, to tackle that. So that has to be reduced, right? So all of the different industries have to be reduced. When we calculate the transportation of the equipment to the site, we're using a model that uses diesel engine transportation trucks to get there, right? The entire system has to change, right? And every part of it. And therefore, if you do the numbers and you look at if everything is changing to a reasonable amount, then what is the impact of CO2 capture? It's extremely positive, right? It's so just like, I mean, if you're against something, you can figure out a way how to write something against it. I just don't.
I find it interesting because the people who are against it, these are climate action people. So they're climate concerned, like everybody listened to the show, I think. But there's a lot of people that are against certain climate solutions.
Yeah, and I get it.
Very often, it's the only solution is emissions reduction.
If you think of it as a limited amount of resources, then I guess that's how people are looking at it. But I just don't see it that way. I believe we have to tackle all of the buckets, and we have to do it quickly because we only have a certain amount of time before the impacts of climate change are going to overwhelm us. And so that we can, I don't think we can have the luxury of picking and choosing on what we start off and, have 100-year time frame. We have a 20 or 30-year time frame where we got to get stuff done here. So all of the buckets have to be worked on.
I agree. So let's cover one more subject. I think we covered most of the objections. I'm sure there'll be a few more pop up.
Always is.
We didn't talk about DAC, so direct air capture, which is capturing CO2 from the atmosphere, which is interesting because even though it's really the same kind of system, people actually don't mind that one as much as they do somehow. I don't know, the ones that are more efficient from industrial plants. But in any case, Svante is working on that. Tell us a little bit about how Svante is involved in the direct air capture side of things.
Well, we were always hesitant, especially 20 years ago, to go into the business of a direct air capture because we know it's quite challenging and quite expensive to do, right?
Because of that lower concentration.
This isn't the BECCS, the bioenergy capture and storage. Not that DAC. This is actually engineered capture straight out of the air. So we didn't go into the business. So you won't, if you Google Svante, you won't see us selling credits for a direct air capture system. But we did go into developing the technology for it in a pretty big way. The underpinnings, the science behind direct air capture, and really tried to push forward on improving the economics of direct air capture, and we've done that in a big way. And we built
the absorbent material.
Yeah, with the adsorbent material, absolutely. Most direct air capture companies are using adsorbents. By the way, there's a handful that's not, including Carbon Engineering, which is a bit of a brute force method that they're using. But most are based on adsorbents, right? And that's where we excel.
So the same concept of what we just talked about, except instead of passing a flue gas, you're just passing atmospheric air through it.
Absolutely, yeah. So you can imagine you got to pass a lot of air to capture any significant amount of CO2, right? Because there's not much in there. We've built a manufacturing plant, a large one, to build these filters, so we can cater and get the cost down to building these plants to companies. And that's how we're doing it. We're catering to quite a few different companies at the same time on supplying technology, supplying know-how, supplying equipment for these projects. Now, I understand why people are more all right with direct air capture. And I think it comes from the fact that the CO2 is already in the atmosphere. We've already done the damage. So we're trying to go backwards. And I get that. That makes a lot of sense. We're trying to fix the damage we did in the past. My challenge to that, to some extent, I do think we have to do both at the same time, but we can't do DAC without doing point source, because if you don't tackle the source of the CO2, you're really chasing your tail, right? You're chasing your tail
so much easier and cheaper to get it before you put it in the atmosphere than to take it out.
This is a classic example where we have to do both, right? Like if we just did direct air capture, we did the most expensive type of capture and still spewing CO2 into the atmosphere with smokestacks. How does that possibly make sense, right? So we really do have to do both. And I think, especially later on in the 2040s and 2050s, turning back the tide and fixing some of the damage we did in the past by direct air capture will be a very valid endeavor. To do that. So, we're involved in that in a big way. We're very supportive in the industry on that. There is companies that are willing to pay for direct air capture and the credits, and that's driving the industry forward on that. I think it will be part of our mitigation tools. We have to have a lot of tools in the toolbox, and that will be one of them.
Okay. So, Brett, so now we're going to go to our, bring in our co-mods to ask some questions, and then also maybe take some select questions from our YouTube crowd. So I'm going to invite Stacy in here. Stacy, whoa, let's get Brett to be the big guy. There we go. Yeah. Stacy, welcome.
Hi, good to see you, Dan, as always, and Brett, nice to meet you.
Nice to meet you.
We've had a little bit of chatter, but mine is, it's funny because Dan has been saying you're going to be on for a number of weeks, I believe, but this week would be really interesting since the EPA is going to potentially stop industrial polluters from having to report their emissions. So I don't know. I just thought that.
But they haven't backed off on carbon capture, actually. In fact, this 45Q thing we talked about, it was first signed by Trump in his first term. Yeah. So it was actually passed by Republicans and Democrats, by the way. But so that one, which is different than the reporting, which is they just want to pretend climate change isn't real. So that's not going to work.
So that doesn't. So you're not sweating it. Or whatever.
Well, I wouldn't say that. I've been in this space a long time. I've seen a lot of ups and downs. Like I said, I think this is more about psychology than anything to do with climate change. And it goes in waves. It goes. There's pushback at some point at some points in time, and then there's a real a surge of activity and desire to deal with climate change. It kind of goes up and down, but it never disappears. It's always going to be more, I believe, because climate change doesn't care about what we think. It's happening anyway. So the impacts will be always there, and it's normal for it to go up and down, and depending on the other things that are happening in the world for that. So I long term, I don't have an issue. I do think it will have an impact to some companies and some technologies in the short term that won't be able to get past this challenging time on this. That will happen. Maybe that makes the companies stronger, the ones that make it. I don't know, but there will be an impact, and we're concerned. We're a for-profit company. We want to grow and deploy technology and North America is the largest market in the world. So yes, we're concerned, but I think it's going to march forward.
Okay.
We produce the most garbage for sure. That's
So,
we had. Do you want to go to Eli? Is he here?
yeah,
Or
let's go to Eli for a question, and
Okay.
we'll come back for
Okay.
the YouTube questions. So,
Gotcha.
hey, Eli, whoops, doing that. What's your question for Brett?
Thanks. Good to meet you, Brett. You've used the analogy of we got to stop throwing our trash on our neighbor's lawn, and that's externalizing costs in a variety of ways. This is the framework that we've had from the IPCC, which was in fact based on a certain estimation of climate sensitivity, which we've learned in the last couple of years was actually underestimated just how much warming we are experiencing from greenhouse gases and CO2 in particular. And that makes the situation that we're in, our understanding of the future that awaits us on the current path, to be much more concerning than it might have been before, and even more than what we're seeing unfolding already. And on top of that, feedbacks appear to have also been underestimated. So it's not really just not littering on your neighbor's lawn to be a good citizen. The fact is, the whole town is knee deep in litter.
So what's your question, though, Eli?
So from your discussions with people, which of course have to take into account the cost, if the real challenge is not just to zero out emissions, but to get into negative and hopefully deep negative carbon fluxes, how much more do you think the costs forward to make negative emissions a reality as soon as possible?
Oh, I would say that negative emissions, direct air capture, needs to get down in around 300, in around 3 times what point source would be.
So $100 a ton for point source capture and 300 for
300 for that. I think those would be real reasonable numbers that would allow for large deployment of both. Now, if we could get to 50 and 150, that would be even better, right? I mean, that would be the long-term push towards that. By the way, it's never going to go to 5, 10, 30, those kind of things, right? It just, physics doesn't allow that, in my opinion, and many other people's. But if we could push towards 100 and 300, or 50 and 150 in the long term, I think that would allow for long-term deployment. As it is right now, you're looking at, in general, for engineered direct air capture, you're looking at, in around $1,000 per ton. It can be a bit lower, a bit higher, but that's generally what you're looking at. I think that's too high to integrate into the garbage analogy, if you would. That there needs to be progress on that.
But also at a tiny amount. Yes. Where that literally needs to scale. I did, look by a factor of 1 million times more than it is today.
So scaling itself helps with the cost, and then and also, if everybody thinks that this is going to happen and there's going to be a market, then everybody works on it, right? Like that's the other thing, where if people believe that there's going to be opportunities in this space, then the people like me that are in their garage with ideas, they start working on it, right? And you'll have more and more ideas and more ability to get down that cost curve. Mm-hmm. So it's kind of, it goes hand in hand, right?
Yeah. So the policies are put in place to fund deployment. Yeah. Then a lot of people will work on it, and they'll figure out, first of all, it'll get bigger, and there'll be natural economies of scale as you go. And
then there'll be new technologies that we can't even think about that come online in the next 10, 20 years, right? So
solar dropped in cost by 99%, like in like
It's
30 years.
unbelievable, right? I mean, you wouldn't even have, most people wouldn't have guessed that, right?
No one did.
Before. It's just amazing. So yeah, the potential is there, even though it's hard to see right now, right? But it's certainly there. But I don't think we're all that far away from it. I think we're very close in point source to it, and in direct air capture. If there's more scale up done, I think we'll get closer and closer to the numbers where it can be deployed in a big way. Does that answer your question a bit? I mean, it's a very open-ended question you had.
Yeah.
So
okay, well, thanks,
you.
Eli. And we're going to go back now to Stacy. We're going to walk through some. Well, keep putting me in there. Walk through some of the questions in the chat. And I saw one from Martin. Should I pull that one up?
Oh, yeah, there are a couple. Yeah, Martin's on fire today.
Yeah, so Martin, and I just saw this too, and I answered this on Twitter already, so I know the answer. A new study just came out limiting the global CO2 storage to about 1,460 gigatons rather than the 14,000 to 20,000 that the IPC assumes. Does that play a role for you? Did you see this study, by the way?
I did, yes. There's seen a lot of studies though over the time, and there's always quite a few assumptions that are put in these types of studies. Whether those assumptions are correct or not is always the question.
Well, it was basically saying we won't want to put it anywhere near a city. We won't want to do anything like that. So they just kept reducing.
You're coming up with practical assumptions that reduces the amount that you can practically do, which I mean is a valid question. I think is that how much will it's another psychology question, right? Is that 20 years ago, believe it or not, Germany was at the forefront of CO2 capture, had 20 pilot plants going. They were the leaders by far. Well, they, in about 2008, I think it was, I might be wrong on the year, but they put a moratorium on CO2 sequestration. It stopped it in their tracks. It was all about psychology, right? It wasn't at that time about really science and stuff. It was just about psychology. So just like policy frameworks and everything else to do with climate change, do we eventually say, no, we need to put CO2 everywhere we can underground?
Yeah, and by the way, I looked it up myself. So just so people know, by the way, what you do is you actually compress the CO2 after you capture it and get it sort of in a liquid form because it's dense, and you send it down a pipe into a saline aquifer. And
very deep.
There is a lot of room underground. It's hundreds of times more than we need, unless you do these exercises where you just try to cut it back everywhere possible. And then, by the way, 1460 is still an incredible amount.
That's a big number to start with.
Keep us very busy for the next 30, 40 years. But on top of that, there's another, I looked this one up, there's another way to store CO2, and this is what Climeworks does with their direct air capture system, is you mix CO2 with water and make club soda out of it, and then you put it into basalt soil formations, which exist all over the world, and that turns it into rock. And I looked up the numbers there. There's 100 to 300 trillion tons of capacity just from basalt, and that's separate from this other study, which was really just looking at the deep injection wells.
Aren't there ones that filter it, and we're making diamonds and carbon fiber?
The diamonds don't use a lot, but you could do that. You could make things out of it, but the numbers are so huge that you really can't make anything. I mean, you can make cement and maybe carbon fiber, but that's still only gigatons at best. We need actually. So the total amount, the most we need, is 2.6 trillion tons, because that's the total we've emitted so far. Let's say we get up to 3. So the most we need is 3 trillion tons. Unless the world's going to be over if we get beyond 4 or 5 trillion. So we need at most 3 trillion, and that's 100 to 300 trillion. So we need a tiny fraction of just the basalt. And of course, even with the terrible assumptions in that study, even if they're all true, you still have essentially half of all emissions can still be put away that way.
Yeah.
And by the way, we didn't even talk about nature-based solutions today. which whole other ways of capturing CO2 out of the air and things. So there's not a limit on where to put it.
I
think
am
the
not
bottom line.
concerned at all about the availability of space for sequestration underground. In that, I don't think that's a barrier for us. I mean, you can come up with different numbers and expectations, but if we really want to, we can put all of our CO2 underground for a long, long time.
Yeah, but
My biggest worry is how fast we can put together policy frameworks that actually make real action happen on all fronts, not just CO2 capture, but on
I agree. This has to be done. There's not going to be any way around it, but it's a lot easier to either not make it in the first place,
yes,
or when you think about actual trash, it's like I want everything to go in the blue or the green bin. I don't, or to reuse it somehow, not to go into the landfill, which is the way I'm looking at the carbon capture and sequestration. It's like when you're sequestering it, it's the dump. It's done. And we don't ever want it to come out again versus, what else could we do with this?
Not make it. Not
Yeah,
well,
not
yes.
make-
The CO2 utilization, yes, everybody would love for CO2 utilization to be a big thing. You run into physics is the problem with that. CO2 is very, very difficult to turn into something else. It usually takes an enormous amount of energy to do that. And
to
you can
separate.
Well, you're
the
basically
C and the
unburning
O2.
the CO2.
just to turn it into something else.
Gotcha.
Takes the energy. So you're kind of chasing your tail in a lot of circumstances with that too. So the physics hits you with that. And as everybody would like the CO2 not to be produced. I agree with you. Like if I could go across the river, I can see our cement plant from here, from my house, right? It's the biggest emitter in the Lower Mainland here in Vancouver by far. If we could turn that off, that would be the easiest and best way. It'd be immediate 1 million tons a year reduction in the Lower Mainland emissions, right? It'd be boom, we'd be over.
Yeah.
But what would we build our city with?
Yeah, or how would we deploy renewable energy and windmill?
I mean, when you look, everything we do in this city is based on concrete.
Yeah, and steel.
Okay.
Yeah.
What about Jean wants to know if he can get a carbon capture contraption for his wood stove, or is that making biochar instead?
Yeah, make biochar. Yeah,
You could theoretically we'd make small systems, but the economies of scale would make that cost per ton be thousands of dollars per ton.
And then you still have to, what are you going to do with it? You're not going to drill a hole in your own
exactly.
ground
Then
to
you
get rid of
got to
it.
do something with it, right?
No,
So
biochar is the way to go for that. If you want
it's
to
just
do that.
not. That's not a good way of CO2 emissions reductions, right?
Yeah, Jean, you gotta.
But no.
John, you gotta get onto biochar instead of your wood
Okay,
stove.
I'm looking here. Any other that you see, Stacey, that are?
Nope. That
Okay.
was most of it. Yeah.
All right, very good.
I like your cat in the background.
Thanks. That's Rocky. He's our new other co-mod here, I guess. Yeah.
So, Brett, this has been a fascinating discussion. I think actually it's funny we didn't talk too much about pulp and paper, but that even less in the title. We really just talked about carbon capture in general. But
yeah,
I guess the takeaways here I think are that it is real. By the way, one question I did see in the chat was:
sure.
Are there any real full-scale carbon capture systems in existence today? Like not just demonstrations like we talked about.
Oh no, there is full scale, and we happen to have some here in North America. The U.S. has one on coal power. Certainly not everybody agrees with coal power, but there is a full 5,000 ton per day, which I think is like 1.5 million tons per year, something like that. So full scale, and there we have one in Canada on a coal power plant as well, and we have one on a hydrogen production plant as well at full scale at 1 million tons per year. And the next one online that's full scale commercial is the one in Norway on a cement plant, which is full scale commercial. That just started up now.
So it is early days, but it is real,
and there's many more coming. Yeah, there's many more coming, but there needs to be thousands and thousands of these, right? Because there's a lot of smokestacks.
But at 1 million tons each, I mean, roughly speaking, that that's a really
It
powerful
adds up
way.
fast, right? It adds up fast. So.
It adds up fast because 1 million tons is way more than all the direct air capture.
Oh yeah, yeah, good God, yeah. The point source can add up numbers much more quickly.
Tens of thousands of tons, right? But yeah. So wow. So anyway, it's been fascinating. It's great to talk to you about it and I to share this with the world, because I think there really is a lack of understanding about the reality of carbon capture, what it is, how it works.
There is, yeah.
There's a lot of disinformation out there, and just a lot of people just are just against anything but emissions reduction. We didn't even. That is one of the objections. We kind of talked about it. If you do this, then you won't be doing something else. But I think we have to do everything.
100% we do, right? We're running out of time. We need to tackle it all. We have the tools. I would say what we need more of in the world is the desire.
Yep. That's a very appropriate way to end. As we cover on Climate Chat, we don't just cover climate science and climate solutions. We talk about the psychology and all the other communications issues of how to drive climate action.
Barriers.
We can do these things if we choose to. So that's a great comment to end with. So, Brett, thank you so much for being here. And we always forget to say it, but like and subscribe, everyone out there, if you like this content, and share it with your friends, and so we can help spread it. Climate information is not spread as much as cat videos and things like that. So let's all help make it be a little more broad. And thanks so much for being here, Brett. And
thank you, Dan, for the support now and over the years, and for doing this. Thanks for everybody involved in this and everybody watching, and anybody that wants to reach out and ask more questions can always reach someone at Svante, maybe me, but someone at Svante. Thank you very much.
And links are in the description. So, and Brett, you can hang on here for a moment, and we'll see everyone else next time. Bye-bye, everybody.
Bye.